Ryan, Connor, Grace. An intro, if you please.
It's time for Maths with Mr. Thomas.
Here we are, chapter 13, lesson number 10. This is the review lesson for the vectors chapter. This does not include every slide or every example. It is just me going over the key points from all the individual lessons. If there is anything though you want in more detail, look back at these individual lessons. So to start with, there was a recap. We were introduced to vectors back last year in National 5. So I started going over all the work from National 5 very quickly. So remember, there's two types of measurable quantities. There is a scalar, and there is a vector. A scalar is something that has a magnitude or a size, and a vector also has a magnitude or a size, but it's also got a direction. For example, gravity or force or velocity. We then looked at naming vectors, and the way you can draw vectors out, the way you name them, is you take the letters at the end of the line. So we've got AB. We can also call that vector U, where it's going to be underlined, or we can use a bold letter when you see it typed. When you multiply a vector by a scalar, the direction will remain the same, but the magnitude or the size will change. So here we've got vector u. If we've got 2u, well, it's 2 times the length. 3u is 3 times the length. If it's negative u, well, it will be parallel, but it will be going in the opposite direction. So the negative makes it go back the way. After that, to add vectors, we were looking at adding them, and you have to do that tip to tail. So here, where one vector ends, the other one will start. And if you want to draw in u plus v, well, that was the very start of your journey, that is the very end of your journey, and it's really just the shortcut to go from here to here. If you subtract vectors, well, you add the negative of one of the vectors. So if you have something like u minus v, well, it's really u plus negative v. And remember, negative v is the same vector, but it's the opposite direction. So here you would have vector u, and then if you subtract v, you're adding on the negative of v, and again, that's the very start, that's the very end of your journey, so just draw the shortcut going from the start to the end, and that will be u minus v. You can represent them on a grid system. Here they are drawn out. We have here the vector AB, and you're going along 4 units and up 3, so you would have the components 4, 3. To go from C to D, well, you're having to go back 4 boxes, and you're going down 5 boxes, so that would have the components -4, -5. After that, we were looking at adding and subtracting and multiplying vectors, and to do that, really write them out in component form. So you have one number, the next number, possibly the third number above one another, and you're just wanting to add your x's, add the y's, and it's as simple as that. If you're subtracting, just subtract the x's and subtract the y's. If you're multiplying a vector by a scalar, so if you're multiplying it by a number, all you're doing is you're multiplying each of the components by that number. So here, 3 times -2 is -6, 3 times 5 is 15, so that will be 3a. If you're halving the vector, well, really, you're multiplying by a half, so multiply each of the components by -1/2 in this example. After that, we were looking at position vectors, and the position vector for PQ is given by Q minus P. As you can see there, to go from P to Q, one way to work that out is to have OQ minus OP, or as I just said, you write it as Q minus P. So if you have two vectors A and B, to work out the components of the vector AB, the vector between A and B, you're just wanting to take the components for B and subtract the components for A. So B minus A, and you will end up with the vector AB. After that, how do you get the length of a vector? What do you do, Sandy?
It's the magnitude!
Brilliant, it is the magnitude, and how do you work it out?
Square root!
Brilliant, you're wanting to take the square root. So if you want the magnitude of, for example, here, EF, first of all, work that out. So work out vector EF by doing F minus E, and to get the length, as Sandy says, that will be the square root of each of the components squared and added together. So here, the square root of 6 squared plus -8 squared, work that out, and you will work out the length of EF. And the way you write it is by using these magnitude or modulus lines.
Ooh.
After that, we were looking at alternative vector journeys, again something else from National 5. And for this, really, you're wanting to only use the paths that you know. So in this example, to go from E to F, that was vector A. To go from E to H, that's vector B. It was telling you in the question that to go from H to G, well, that there would be 4 times vector A. So you'd have 4A to go from H to G. It's the same thing for each of these examples. You want to think, how do I go from that point to that point, the start to the end, but you can only use these routes that you know. For example, to go from E to N, well, you can't go along here and then up here. We don't know this vector, so you've got to go up here to H and then along to N, and N is half of HG. So you can work this out. Have a look back at that lesson if you're wanting it in a bit more detail. Vectors, you can flip them to 3D, which we have already done with National 5, but instead of just an X and a Y coordinate, we've also got a Z coordinate as well. So you've got your X axis, your Y axis, and the Z is really going to be the height, if you imagine the X and Y plane as just being perfectly flat. So you can write a vector out using 1, 2, 3 components, your X, your Y, and your Z. The good thing is, if you do have vectors in 3D, everything from 2D remains the exact same. To add vectors, well, you're still adding your x's, your y's, your z. To subtract them, you're doing the same, but subtracting. To multiply by a scalar, well, again, you're just multiplying each of the components by that scalar. To work out the position vector AB, it's still b minus a. To get the magnitude, it's still the square root of that squared of that squared of that squared, and so on. Everything from 2D remains the same for 3D. We then moved on to look at unit vectors, which was lesson 2. And for every vector, there exists a parallel vector u of magnitude or length 1. So here, if you have a vector v, well, you could say, right, there's going to be a vector that's the same length. Sorry, not the same length, the same direction as that, but it's only got a length of 1. And that would be known as a unit vector. If you do have a unit vector, then the length of it is 1, which means if you work out the square root of the components squared, so here you've got L, M, and N, so the square root of L squared plus M squared plus N squared, that's just going to be 1. And if you square both sides, you'd have L squared plus M squared plus N squared, and that equals 1. So if you do square the components and add them together and you get 1, then you know it is going to be a unit vector. For example, here find the components of the vector u parallel to vector v if v equals 3, 4. To do that, well, you've got your vector v, which is 3, 4, so you're going along 3 and up 4. Get the length of that, first of all, thinking about the magnitude. So to get the magnitude, it's the square root of 3 squared plus 4 squared. That will then give you 5 units. The unit vector will have the same direction, but the length will only be 1. So how do you go from 5 to 1? Well, you divide by 5, you would take a fifth of it. So the unit vector would be a fifth of the length of v. So you can multiply this vector v by 1/5. Multiply with the scalar, so you'd have a fifth of 3 and a fifth of 4. So you'd end up with 3 over 5 and 4 over 5 for the components. Here we're looking for 2 unit vectors parallel to A. So first of all, again, you needed to work out the length. Work out the length of this vector. So the square root of 12 squared plus 3 squared plus 4 squared. That will give you the square root of 169, which is 13. 2 vectors that are parallel to that, but unit vectors. Well, remember, to get the unit vector, you have to divide by that length. So you would divide by 13. So you'd have 12 divided by 13, 3 divided by 13, and 4 divided by 13. That would give you 1 of the unit vectors, but you can also have the negative. You could have the same length, but the opposite direction, which is why you'd have a plus and a minus for that. That will give you the 2 unit vectors that are parallel to A. Here, we were told we had a unit vector, we had to work out 2 possible values of A. If you have to work out possible values of A, well, you know, just from a few slides ago, if you have A squared plus 1/3 squared plus negative 1/3 squared, you will end up with 1 because it's a unit vector. From there, you can then rearrange that to find the values of A. After that, it was asking you, is this a unit vector? Well, once again, similar to the last example, if you square each of the components, add them together, you should get 1. And in this case we did, which means that was a unit vector. We then went on to look at the unit vectors I, j, and k. And these are 1 unit long. I is 1 unit, and it's the length of the x-axis. It's going along the length of the x-axis. J is going along the length of the y-axis, and k is going along the length of the z-axis for 1 unit. Any vector can be expressed as a combination of these components. So if you have a vector v, which is 3, 4, 2, it means you went along 3 units in x, you're going back 4 units in y, and you're going up 2 units in z, which means you can write it as 3i plus 4j plus 2k, and any vector can be written like that. For example, if you have a vector v, which is 4i minus 8j plus 3k, well, you can write that into components with the 4, negative 8, make sure you put in the negative, and then 3. For BC, if that is the vector 7j minus 2k, again think about the components, so you're thinking about the coefficients of I, j and k. There's 0i, which is why we're starting with 0, then you've got 7j and negative 2k, so you can write down those 3 numbers. Express each of these in the form I, j and k. To do this, you have r and you've got gh. To do that, really you're wanting to take these values here. That will be the coefficient of I, that will be the coefficient of j, and this number here, the negative 1, will be the coefficient of k. And very similar for this example. Example 7 in that lesson, the vector A has these components. Find the unit vector u, which is parallel to A, and writing your answer in the I, j and k form. Once again, you need to work out the length of this vector here. So it's the square root of negative 3 squared plus 0 squared plus 4 squared. That'll give you a length of 5. And then to get the unit vector, you're wanting to divide the length, the vector by its length. So you'd have negative 3 over 5, 0 divided by 5 is just 0, and then you take that 4 divided by 5 as well. Writing that in the form of I, j and k, that's the coefficient of I, that's the coefficient of j, so we don't even need to write it because it's 0, and that is the coefficient of k. We're then moving on to look at parallel vectors. Before we look at collinearity, we have to first understand that parallel vectors, which is why I put in this lesson. So if you have a vector u, so let's say it's x, y, then ku will be kx, ky. You're multiplying both x and the y by k. Vector ku is parallel to u, you can see that there, and really, if one vector is a multiple of the other, then the two vectors must be parallel. We went on to some examples with that. Example 2 in that lesson show that these two vectors are parallel. What you want to do to start with is take out the highest common factor in each vector. So with vector A, you had 6, negative 2. Well, you can divide both those numbers by 2, so take 2 outside the brackets, and it's 2 times 3, negative 1. For vector B, 21, negative 7, you can take the 7 outside the brackets, so it's 7 times 3, negative 1. Check for the same vector. Because we've got the same vector, it means you can write one vector in terms of the other, and to do that, you want to use this crossover method. So you would have, let me just write this on, you would have the 7 with the vector A, and you'd have the 2 with vector B. So you can say that 7A equals 2B. From there, just express one vector in terms of the other. So divide both sides by 7, it'll give you A equals 2/7 B. Or if you divide both sides by 2, you'll have B equals 7 over 2, A. Because of that, it shows you that A and B are parallel. You're expressing one vector in terms of the other. Here, example 4, are these two vectors parallel? Well, to start off, take out the highest common factor once again. So take out the 3 in the first one, so you've got 3 times 4, 3. Take out 8 in the second one, so you've got 8 times 2, 1. You need to check for the same vector. Here we did not have the same vector. 4, 3 and 2, 1 are not the same. They are not equal, so the vectors C and D are not parallel. Once you're okay with that, we can move on to look at collinearity. That is really just taking what we learned in chapter 1 a step further and flipping it to 3D. And to do that, you would start to think about your vectors, but it's really wanting to check if 3 points lie in a straight line. We looked at some examples for that, so prove that these points are collinear. Well, the first thing you have to do is check if they are parallel. So, work out AB, work out BC. Just remember, if you end up with something like 6, 2, take out the highest common factor. So we've got 2 times 3, 1. If you do that, then you can again use the crossover method. So you can say 1 times AB is equal to 2 times BC. Because of that, it means that AB and BC are parallel when you're expressing one vector in terms of the other. So we'll start off writing AB equals 2BC. Therefore, AB is parallel to BC. And to check they are collinear, you need that same point. And here, obviously, AB and BC are both using point B. It is a common point to both of these vectors. So you can say then that A, B, and C are collinear. Doing the exact same thing with 3D, prove that these 3 points are collinear. So again, we need to work out AB by doing B minus A. We end up with that vector, we've got the components. Work out BC, C minus B, we get that vector, we get the components. Take out the highest common factor, cross over once again. So 2 times AB is equal to, well, there's a 1 here. If you imagine the 1 in front of the brackets, that'll be 1 times BC. So 2AB equals BC. From there, one vector is expressed in terms of the other. You could always divide by 2, so AB equals a half BC. Because of that, you can say that AB is parallel to BC. Also, same as the last example, B is a common point to AB and BC. They've both got a B in them, so it's common. And because of that, they share a common point, the parallel, so A, B, and C would be collinear. Woo! Are these points collinear? Well, again, you need to do the same thing. First of all, work out AB, work out BC. From there, take out any common factors. So here we've got 2 times -1, -1, and here it's just -2, 1, 5. From that, well, if you think I don't have the same vector and we need the same vector to show they are parallel. So if these lines are not parallel, if the vectors are not parallel, then it means they are definitely not collinear. So you can just finish off by saying these 2 vectors are not equal, so AB and BC are not parallel, and if they're not parallel, they are not collinear. No, no, no. With this one here, this was very much the same, but we had to find the values of A and B. You just start it off the same way. Work out AB, B minus A. Take out a common factor if you can. Obviously, you have to deal with A, which may be a bit of an issue, but practice and you'll be fine. Work out BC, so do C minus B. Again, you're wanting to take out a common factor. What you really need to do is you're needing to get these vectors to be equal. Here, well, there's a B in your Z component and there's an A in the Y component here. The only components that don't have a letter in them would be the X. And because they're the same, well, if they are collinear, which it says in the question, then you know the y's must be equal, so you can say -1 take away a fifth, A must be equal to -5, and you can solve that to find A. Also, the 3 must be equal to the half, B minus 3, which means you can solve that to find B. That's obviously one of the harder examples. After that, we moved into the section formula, and that is when you're wanting to divide a line into a given ratio. There was a wee proof here for the section formula, but what you end up with is to get the vector P, you'd have n times vector A plus m times vector B over m plus n, which is a bit confusing and it's not given in the exam, so I always prefer to think about this wee diagram here. So to work out position vector P, that is going to be, well, you've just got your 2 points, you've got A and B, P is going to be between them, and your ratio, if it's, say, 5 to 7, you'd have a 5 here and a 7, so that is just the numbers from the ratio. There is also a wee bit about dividing a line internally or externally. If a point divides a line internally in the ratio 3 to 2, then it means you're coming over 3 units to get to P, and then 2 units to get to B, and P will lie between A and B. If P divides AB externally in the ratio 3 to 2, then it means to go from A to P, once again, you're going along 3 units, but P does not lie inside AB, it lies outside, it's external. So if it divides externally in the ratio 3 to 2, then to lie outside, you have to come back the way 2 units. So you would write that as 3 to -2, or -3 to +2. The negative can go with either number. Again, it's part of the trickier questions. With this example, we had P dividing AB in the ratio 3 to 2. Find P given that A is that point and B is that point. To work that out, write down what you know first of all. Well, you know to go from A to P and then from P to B. That is the ratio 3 to 2. We know the 2 points, they are given. This is the formula. You can either memorize that or maybe think about this wee useful diagram. We've got the 2 points, A and B, so just write them down. Point P is going to lie between them and the ratio is 3 to 2. So we've got a 3 to 2. From there, really, you're kind of just cross multiplying here. You're doing 2 times this vector A. So if you write it out, these will be the components. So you'd have 2 times the 2, -3, 4. And then you're adding on 3 times the vector B. So 3 times 12, 7, and -1. And you divide that by mn, which is going to be m plus n, which is 3 plus 2. From there then, multiply these vectors by the scalars, add them together, divide by 5, which is really multiplying each of the components by a fifth, so we get the 8, 3, 1. Because that is the vector we worked out, just check if you are asked to work out the coordinates, you would write that therefore as 8, 3, 1. Just write it out in brackets with the comma between them, and P will have that point there. With this example, find the coordinates of the point dividing the line EF internally in the ratio 1 to 3 and externally in the ratio 1 to 3. So first of all, because it's internal, we know to go from E to P, then from P to F, you'd have the ratio 1 to 3. Write down the 2 points, we know them. Again, you can either memorize this, or you could think about this wee crossover method. So you'd have A and B, that's the 2 points. In this case, it's E and F. The ratio M to N is just going to be 1 to 3, and from there 3 times vector E, add on 1 times vector F, and divide by 1 plus 3, so you get down to this. That will then give you the position vector P, so you'd have 6, 4, 4, and if you want to write down the coordinates, well, you can just write it out in a line, so you'd have 6, 4, 4. Dividing externally in the ratio 1 to 3. Well, remember, when it's external, the point is not going to lie between E and F, it will lie outside EF. So you have to put a negative with one of these numbers. You can just put a negative with the smaller number, so I'm putting a negative with the 1. So it would really have negative 1 to 3. Just check if you do have the words internal or external. Whenever it's external, you have to include a negative with one of the numbers. It doesn't matter which one, you will get the same answer. Try both ways if you don't believe me. From that, here to go from E to Q, then from Q to F, I'm putting the ratio as negative 1 to 3 because it's external. I've still got the points E and F, and again, this is the formula, or use this wee diagram where you've got A and B, you've got this point P and M to N. Here I don't have A and B, I've got E and F, but it's still 2 points. I used point P in the last example, so I'm going to use Q, and the ratio external, so negative 1 to 3. Same thing, crossover, 3 times vector E, negative 1 times vector F, so here the negative 1 just makes the plus and negative. From there, multiply by the scalar, subtract them, and then divide by 2. From there, you'll get position vector Q, which means then that the point would be 3, negative 2, negative 5. After that, we were looking at vector diagrams. So vector diagrams is something that we looked at in National 5, but here we're kind of flipping it to 3D. So here with this example, we have this pyramid. Woo, fancy. And we know AB, so we are told that vector to go from A to B. We are told the vector AD, so we know to get to A to D, it will be that vector here. We'd have the components negative 2, 10, negative 2. And to go from A to V, so away up here, woo, going in that direction, you'd have vector V. What you want to do with these vector diagrams, you look for any vectors. If you have an equal vector, it's the same length, same direction. So to go from D to C, well, that will also be this vector here, the same as AB. To go from B to C, it's the same length, same direction, so we also know that vector there as well. The ones that we don't know, though, we don't know to go from V to B because we don't have anything that's that length and that direction. Remember, you need the same length and the same direction. We don't have anything to go from V to D or D to V, and we also don't have anything to go from C to V. So for example, if you have to go from C to V, so we're starting here and we want to end here, well, I always imagine this as roads or paths. You can only go along these paths that you know, so how would you get from C to V? You can't go there directly because you don't know that vector. One way of doing it is you could go from C all the way down to D, which is the same as the negative of AB, which is where that comes from. You could then go from D down to A, and that is the same as negative AD, one of the vectors you know. And then once you're at A, you can just go straight up to V with the vector AV, which is where this comes from. Write down the components then, so you'd have the negative of AB, so it's a negative of 8, 2, 2. You're taking away against the negative of AD, so you'd have take away negative 2, 10, negative 2, and then you're adding on AV. Just add these together, and you would end up with negative 5, 7, which would be the vector CV. Next example, we had this cuboid. Express VT in terms of F, G, and H. So we can see that F is going from S to R. From S to W, it is H. And from S to T, that is vector G. Once again, have a look, see if you have any same lengths, same directions. So here you can see from S to W is the same as from W to X. That will also be vector H. From R to V, that will also be vector H. It's the same length, same direction. And from U to Y, same length, same direction as H. So these will all be vector H. It's very similar for T to U. That is the same as going from S to R. So that vector there is the same as this vector here. It's the same length, same direction. They're all going to be vector F. You can hardly draw on this with a mouse, but you get the idea, they would all be the same. And for vector G, S to T is the same as W to X, it's the same as V to Y, and it's the same as R to U. Look back at this lesson in the notes if you want it in a bit more detail, but really to go from V to T, well, you'd come down here, which is the same as negative H. You would come back the way for F, so it's negative F, and then you go in that direction for G, so you would end up with that answer. We then looked at multiplying vectors, and to multiply vectors, well, we'd only multiplied them by a scalar. Here, what we were doing is multiplying two vectors together, and we found that you can either get a scalar when you do that, or you can get a vector when you do that. If you end up with a vector, really you would write it as vector A times vector B, so you use the time sign, you need that time sign, need the time sign, and that is known as the vector product. That is going to be something that is introduced in advanced higher maths when you multiply them together and end up with a vector. What we do in higher maths is we multiply them together, but we end up with a scalar. And to write that, you would have vector A times vector B, but you don't use the time sign, you need to use a dot. Okay, the dot represents the scalar product. That is what you get when you multiply the vectors together and you get the result that is a scalar, sometimes known as the dot product. We tried some examples with that after I introduced the formula. So the formula for the scalar product is A dot B equals the magnitude of A times the magnitude of B times cos theta. What is theta? Angle between them. Brilliant, so it's the angle between the two vectors, and the vectors have to be tail to tail, as you can see here. The scalar product, the result is a scalar, it's not a vector. And also, if A and B are perpendicular, if they're at right angles, then A dot B is equal to 0, since you would have the cos of 90 here, and the cos of 90 is 0! Brilliant! So you'd have the magnitude of A times the magnitude of B times 0, which just gives you 0. Sometimes though the angle is not given, you may just have the components for the vector, so you use another formula, and this other formula is one that you would use. It's also the scalar product, and that is A dot B equals, you'd multiply the x's together, multiply the y's together, multiply the z's together, and add them together. We tried some examples with that. So here it was calculate A dot B for each of these following diagrams. So we went through them one at a time. Here we had the two vectors. They were pointing away from the vertex. We knew the length, we knew the angle between them. So it's easy as just substituting those values into this formula. Magnitude of A, magnitude of B, so the length of A and B multiplied by cos of the angle. From there, if it was non-calculator, just make sure you know cos of 60 without a calculator, and that would be 12 times a half, which would be 6. For this diagram here, well, they were at right angles, and remember, if they're at right angles, then A dot B is always going to be 0, because you'd have the cos of 90. Cos of 90 is 0, so A dot B is 0. Example C, again, we had the two vectors. They were pointing away from the vertex, which is what we want. It's 120 degrees between them, and we know the lengths, so we can just sub them into the formula. Here we had the cos of 120. If you're unsure about writing that with exact values, look back to that lesson. But really, it's 120 degrees. That's in the second quadrant. Cos is a negative, so you get the negative cos. And the size of the acute angle, well, the distance from 180 is 60 degrees, so it's the same as negative cos 60. From there, cos of 60 is a half, so it's negative a half. And you multiply that by the 2 times 1 to get negative 1. With this example here, the only difference with this is that one of the arrows is pointing towards the vertex. So what you do is you slide your vector down. Whee! And if you do that, well, you're keeping the same length and the same direction. and you're then changing the angle really. It's the angle between them when the vectors are pointing away from the vertex. So doing that, if you just slide that down, obviously you've got a straight line there, so you know that's 45 degrees in here, well you can work out this angle as well, and that will give you 135. So to work this one out, you have these two vectors, you know the lengths, and you know the angle between them would be 135. So just check which direction the arrows are pointing. We did some more examples with that. This one was pretty much the same, but we had radians. If you have radians, it's best to probably think about what that would be in terms of degrees. Think about your exact values and then work out your answer. There's no difference, you're still using the same formula. Here, we were not given the angle though. Oh no! So, in that case, we have to use the other formula. This one here, a dot b equals a1b1 plus a2b2 plus a3b3. Thinking about the vectors in component form, really you're doing 3 times 2, negative 2 times 0, 1 times negative 1, and you're adding the result of each of them. So a dot b, your scalar product, would be 5. With this one, we had to work out u dot v, but to do that, we need the components of the vectors u and v. So in this case, to work out u, well, it told us u is pq, so we have to first of all work out pq, that's q minus p, work that out, and you would get the components negative 3, negative 4, negative 5. For v, it told us that that is qr, so do r minus q, we get the components, and we'd have 3, negative 7, negative 3. From there, once you have the components, you can then go into the formula u dot v equals, and multiply the x's together, multiply the y's, multiply the z's, and then add them all together. So we'd have u dot v equals 34. From there, well, we had that formula, a dot b equals the magnitude of a times the magnitude of b times cos theta. If we rearrange that, we end up with cos theta equals a dot b over the magnitude of a times the magnitude of b. And what that lets us do is work out the angle between two vectors. Note, theta is the angle between the vectors, and you have to make sure that the vectors are pointing away from the vertex, and the largest value you will get for theta is 180 degrees. Here the two arrows were pointing away, so theta is just 60 degrees. Here one arrow is pointing in, one's pointing away, so you have to slide this vector over, keep the length the same, the direction the same, and you know then you would have 120 degrees between them. Here both vectors were pointing in, you need them pointing away, so you're sliding that vector over, keep the length the same, keep the direction the same, but you'd end up with 60 degrees between them. You just have your vertically opposite angles if you imagine your straight lines. If theta is 90 degrees, then a dot b equals 0, once again because cos 90 is 0. Or if a dot b is 0, then it means the angle between the two vectors is 90 degrees, they are perpendicular. We tried some examples with that. So here we had two vectors a and b, and we had to work out the size of the angle between them. First of all, write them out in component form, just like this. After that, work out a dot b, so do 1 times 2, add 2 times 3, add 2 times 6. That gives us 20. We're also needing the magnitude of a and the magnitude of b, so get the length of both a and b, so that's a square root of 1 squared plus 2 squared plus 2 squared, and the magnitude of b, it's 2 squared plus 3 squared plus 6 squared. That gives us 7. From there you can sub them into this amazing wee formula. Woo! And we get 20 over 3 times 7, which is 20 over 21. To work out theta, do the inverse cos of 20 over 21, and you get 17.8 degrees to 1 decimal place. Example 2, show that the vectors are perpendicular. Well, if they are perpendicular, something you need to know is that a dot b must equal 0. So here, multiply the x's, multiply the y's, multiply the z's, add them together, and what do you expect? 0. And that proves then that a is perpendicular to b. As it says here, you don't need to work out the length of a and b. A dot b will be 0 because you can have 0 divided by something. So you're needing that 0. You don't need to work out the lengths. Another example here, it told you that these two vectors are perpendicular and you had to work out the value of p. So instead of a number being the coefficient of I, you had a letter. But once again, you know if the vectors are perpendicular, a dot b equals 0. So write them out in component form, and then from there you'd have 2 times p, add negative 5 times negative 2, add 1 times 4, that would equal 0 because they're perpendicular, and from there you can solve to find the value of p. Woohoo! Here we had R, S and T, and we had to work out the size of the angle. For this, you're best going off to the side and just doing a wee sketch. It doesn't have to be accurate, it doesn't have to be in a coordinate grid, just do a wee sketch, just draw the two vectors. Have the arrows pointing away, and S is going to be the vertex because it's angle RST. From there, work out the size of the angle by first of all working out these two vectors SR and ST. So to work out SR, it's going to be R minus S. That'll give us 1, 2, 1. ST will give us the components -1, -2, 1. And from there, that's just what we had in the last page. But you can now work out the A dot B, the scalar product. So work that out and you get -4. Work out the length of A and the length of B, so you get √6 for each of them. Put them into the formula, cos theta equals A dot B over magnitude of A, magnitude of B. Here we get -4/6. Because it's a negative, well, if you think about cast, when cos is a negative, only between 0 and 180 degrees, well, it's not between 0 and 90. There it's a positive, and it's a negative between 90 and 180. So you know then that the angle must be between 90 and 180. Don't be fooled by the diagrams. This is you just going off to the side and sketching it. You don't know what size the angle is, so you're really just finding out. But the negative here is telling you it's between 90 and 180. Work out the size of the acute angle. Do cos to the -1 of just 4/6. Ignore the negative and you get 48.2. From there, to work out the size of the angle, well, that's the acute angle, so do 180 minus that and you get 131.8 degrees. The last lesson was looking at the properties of the scalar product. Some of these we did touch on in previous lessons, but this was just summing them all together. As I just said, if you work out A dot B and you get cos theta, theta is between 0 and 90. Well, where is cos? What sign is cos between 0 and 90? Well, it's positive. So really, you're going to get a positive number, meaning you'd have the length times a positive number. So you end up with, for A dot B, a positive number. If it was bigger than 90 and between 90 and 180, well, cos there is a negative. So you'd have the length times a negative number. So if you get a negative for A dot B, then you know the angle will be between 90 and 180. And I'm sure you're all aware, if it's 90 degrees exactly, you'd have the cos of 90, and the cos of 90 is 0! Brilliant! So you've got length times 0, which is just 0. Other properties, A dot B equals the magnitude of A times the magnitude of B times cos theta. When you're multiplying, you can multiply in any order. So we could also say that's the magnitude of B times the magnitude of A times cos theta. And really, if you worked out magnitude of B times magnitude of A cos theta, well, that's the same as B dot A. So in other words, A dot B is the same as B dot A. Also, it can be shown, there are proofs for this, but if you multiply out the brackets here just the way you did with basic algebra, then that is going to be the same as A dot B plus A dot C. Also, you can multiply out the brackets here. So if you have A times C plus A times D, well, you can write that as A dot C plus A dot D plus B dot C plus B dot D. Really, the rules apply just the same as if you were multiplying out the brackets. The angle between a vector and itself is 0. So in other words, if you've got a vector and you've got another vector itself, imagine the two vectors, one's going to be lying on top of the other, the size of the angle between those two vectors is just 0. So if, for example, if you had A dot A, well, that's the length of A times the length of A times by cos 0. Cos of 0 is 1, so you just have the length of A times the length of A, which really means you have the magnitude of A squared. And the final property, looking at the unit vectors, where you had the length 1, if you work out I dot I was the length of I, multiplied by the length of I, multiplied by cos 0. Remember, it's the same vector, one's lying on top of the other. Cos of 0 is 1, and the unit vectors have a length of 1, so it's really just 1 times 1 times 1, which is 1. Same applies for j and k if you work them out, and since I, j and k are mutually perpendicular, so they're at right angles really to one another, I is perpendicular to j, I is also perpendicular to k, and k is perpendicular to j. So you can say then it'll be the length of I times the length of j, so it's 1 times 1. And because the angle is 90, you would have 0 for cos 90, meaning then you would always get 0 for the result. We tried some examples with that. So here we had to evaluate A dot B plus A dot C. And to do that, well, first of all, write them out in component form. And remember, A dot B, you would have A and B, so you're multiplying 2 times 1, add 0 times 2, add to -1 times 1. And you're adding on A dot C, which is 2 times 0, add 0 times -1, add -1 times 1. Work that out, and you get 0. Ooh! What does it mean if you get 0? Brilliant. It means the vectors are perpendicular, but here we've got a dot b and a dot c. But remember, one of the properties was multiplying out the brackets. If you go back the way and factorise that, well, suppose you could take a as a common factor, so it becomes a dot b plus c. Which means then, because you've got something dot something, it means those two somethings will be perpendicular. So here, a will be perpendicular to b plus c. We tried more examples. Here we had the sides of an equilateral triangle and they were all 4 units long. Evaluate a dot a plus b plus c. So here, just multiply the brackets, so we've got a dot b, and a dot c. Remember, a dot a, it's the magnitude of a times the magnitude of a times cos of the angle between them. Well, between the vectors a and a, well, it's 2 vectors, one's on top of the other, so there's 0 degrees between them, so it's cos 0. For a dot b, well, you've got those 2 vectors there, they're both pointing away from the vertex, and it's an equilateral triangle, so you know that angle there will be 60 degrees. So you'd have magnitude of a, magnitude of b times cos 60. For a and c, for a dot c, you'd have the magnitude of a times the magnitude of c times the cos of the angle between them. But here, one vector is pointing away from the vertex and one of them is pointing into the vertex. So really, you're taking this vector a and you're sliding that over, so it will end up over here. Obviously, it goes off the screen. The length would remain the same, but it'll be away over here where you cannot see. Because that's 60 degrees there, and it would form a straight line if you slid it over, that there would be 120 degrees. So between A and C, if you slid A over, you'd have 120 degrees. Meaning then, you've got length of A, length of C, and then cos 120. Make sure you know your values for cos 60, cos 120. Just use your exact value triangles, and from there you would end up with 16 for A dot A plus B plus C. That was a quick, or a really long, review of vectors. Try some of these questions in the book, see how you get on. But really you're just wanting to apply every piece of knowledge you have of vectors to solve the various problems. Good luck. Let me know if you need a hand.